In this section of the course, we will understand the system of fits, the nomenclature associated with it, and how to decode and apply different types of fits using standards for various applications. So when we talk about mechanical design, shafts and holes are the most common type of features which are generally used for assembly and mating in mechanical design in interfaces. So the interface between the shaft and the hole is defined by a fit, and fit is said to be the degree of looseness or tightness between two mating parts. So if you take any mechanical design which is having multiple parts, it will have shafts and holes which are associated and which is having mating features. So the definition of those mating features is generally done by defining the fit. So if we are having a shaft and a hole as shown over here, the relative difference between the size of the shaft, that is the OD of the shaft, and the ID of the hole will define the nature of fit, the degree of looseness or tightness between these two parts. So generally there can be three distinct types of fits. First is the clearance fit. So clearance fit is when we are having an oversized hole and an undersized shaft. So the shaft is much smaller than the hole, and so when the shaft is inserted inside the hole, there is some amount of clearance. So an example would be the pin in the pin joint of a hinge. So that pin should have some clearance with respect to the hole, and that is a clearance fit. The other extreme is interference fit, in which the shaft is larger than the hole, that is the OD of the shaft is larger than the ID of the hole, and this results in interference. So in this case, if you want to assemble the shaft into the hole, we need to apply some amount of force, and that amount of force is directly proportional to how much interference is taking place between the shaft and the hole. One example is a bearing which is press fitted onto a shaft. So the bearing has an interference fit with the shaft. So the function also is to fasten the bearing onto the shaft, and hence you can see that the functional requirements of an interference fit might be different from that of a clearance fit. And then there is the transition fit, which is the case in which the hole and shaft size are almost the same size, and hence the assembly will not require that much amount of force. You can say that the snug fit is an example of a transition fit. The amount of force required for assembly will not be as high as compared to interference fit, but also there will not be clearance for relative motion between the shaft and the hole as in the case of clearance fit. Each of these types of fits have their own applications in mechanical design. One example of interference fit is the assembly of a ball joint onto the control arm of a suspension. So one arrangement of the suspension control arm is in which the ball joint is press fitted onto the control arm. There are other ways of assembling also, but this is one way of doing it. So in this case, the interference fit has to be defined between the control arm hole and the ball joint OD. Now we will understand the nomenclature which forms the basis for the system of fits, what are the various terminologies, and how to define them. So this is a shaft and a hole assembly. So this small d indicates the basic size of the shaft, and capital D indicates the basic size of the hole. So the basic size of the shaft and basic size of the hole are the same, and D min indicates the minimum size of the shaft possible. D max indicates the maximum size of the shaft possible. So the difference between D minimum and D is lower deviation. It is called as the lower deviation. The difference between D max and D, that is, this is D minus this distance is upper deviation. Similarly, for the hole, the maximum size of the hole is D max, capital D max. Minimum size of the hole is capital D minimum. So capital D max minus D gives us upper deviation. Capital D minimum minus D gives us lower deviation. Upper deviation is always the difference between the upper specification limit minus the basic size, and lower deviation is always the lower specification limit minus the basic size. It is both for shaft and hole. D max, capital D max and small d max both are upper specification limit, and capital D min and small d min are both specification for lower limit. So if you want to define a tolerance zone, so tolerance zone is defined from the lower limit to the upper limit. If you want to define that, then this zone will be that tolerance zone. From D min to D max, that difference will be the tolerance zone. So within this zone only the variation of the shaft can happen. Similarly, same case for the hole. Between capital D min, capital D max, that is the tolerance zone for the hole. So if we are writing the specification for the diameter of the shaft, it will look like this. So D is the basic size, small d is the basic size, and the upper limit and lower limit is defined by minus UD and minus LD. So small d minus UD is nothing but this distance will give us D max, and small d minus this lower deviation will give us D minimum. So when you use this to calculate the limits, we will get D min and D max, and this will define the specification of the shaft. Similarly for the hole as well, capital D minus UD of hole and minus LD of hole. Minus UD will come above. So now we will define a very important term called as fundamental deviation. So fundamental deviation is the smallest deviation from both upper and lower deviations. So in the case of the shaft, you can see that lower deviation is large compared to upper deviation. So upper deviation is called as the fundamental deviation for the shaft. In the case of hole, the lower deviation as shown over here between this line and this line, this is the basic size line and this is the line for the capital D minimum. So that is lower deviation, and upper deviation is larger than the lower deviation. So in this case, for the whole, lower deviation will be the fundamental deviation. This parameter fundamental deviation is very important in the system of fits because it allows us to find out where the tolerance zone is located with respect to the basic size. So if we know the basic size, if we know the fundamental deviation, and if we know the tolerance zone size, then we can define the tolerance specifications for that fit. So that's the whole idea. So in this case, upper deviation for the shaft is fundamental deviation, lower deviation for the hole is the fundamental deviation. So it is very important to understand the tolerance zones for various types of fits. So let us take this example of a shaft and a hole. So the shaft is having a lower deviation as shown over here. The small red arrow is the lower deviation, the larger red arrow is the upper deviation. For the hole, the smaller blue arrow is the lower deviation, larger blue arrow is the upper deviation. So these define the limits, and hence when you define the limits, you get the tolerance zones. So the blue color block is the tolerance zone for the shaft, the orange color block is the tolerance zone for the hole. The relative locations of these two tolerance zones will eventually define the fits. So if we take the clearance fit, so this is the axis of the hole and the shaft, and this blue color block indicates the location of the tolerance zone, which is defined by the upper and lower deviation, and this orange color block indicates the location of the tolerance zone for the hole, defined by the upper and lower deviation of the hole. So over here, the blue color block is below the orange color block, which means that it is a clearance fit. That is, the maximum size of the shaft will be lesser than the minimum size of the hole. So this line would indicate the maximum size of the shaft, and this line would indicate the minimum size of the hole. So this is a clearance fit. Now we will have a look at interference fit. So interference fit is basically the condition in which the shaft is always larger than the dia of the hole. So the blue color tolerance zone indicates the tolerance zone of the shaft. As you can see, the bottom line, which is the lower deviation of the shaft, is larger than the upper deviation of the hole. That means in any case, in the worst case, the smallest shaft will always be larger than the largest hole. It means that this will be a heavy interference fit. And then we can define transition fits. So transition fit, which is tending towards clearance, is this one. So there will be an overlap between the tolerance zones of the shaft and the hole, as you can see over here. and a transition fit which is tending towards interference. So the difference is half of the orange zone is towards upside in this case, and half of the orange zone is towards downside in this case. So since this is transition fit, the amount of clearance and the amount of interference in this case will be much lesser as compared to a pure clearance fit or a pure interference fit. So here an important assumption, important consideration is that the axis of the hole and the axis of the shaft are coaxial. That is, the axis of the hole and the axis of the shaft are always matching. Whenever we are doing this analysis for fits, or when we are using the system of fits to specify a certain specification, we always consider the coaxiality. We'll have a brief look on the shaft basis and hole basis system of defining the fits. So the basic idea of defining a fit is defining the tolerance zones for the shaft and the hole. As we have already seen, the clearance fit, the interference fit, the transition fits, all are dependent on the location of the tolerance zone. So we need to locate the tolerance zone and we need to identify the size of the tolerance zone. These two are the main things when defining the fits. So if we are defining the fit by keeping the tolerance zone of the shaft as fixed, then it is called as the shaft basis. So as you can see over here, this is the axis of the shaft, and this is the basic dimension, and this is the tolerance zone. So the lower limit is equivalent to the basic, and the upper limit is the basic plus this width of the tolerance zone. So this tolerance zone of the shaft is fixed. Then you can define the tolerance zone of the hole. If it is above that of the shaft, then we can say that it is clearance fit. If it is below that of the shaft, it is a interference fit, and in between it is the transition fit. So defining the tolerance zone of the shaft to be fixed and then selecting the tolerance zone range for the hole, whether it will be for a clearance fit, whether it will be for an interference fit, or whether it will be for the transition fit, is called as the shaft basis of defining of fits. And if we are doing this the other way around, that is, if we are defining the tolerance zone of the hole to be fixed, this is the tolerance zone of the hole in orange color, it is fixed with respect to a basic, and the axis of the hole is shown over here. So the tolerance zone size is known, and that is fixed for the hole, and then we select the fit based on the tolerance zone of the shaft, whether it be for an interference fit. In this case, this will be an interference fit, this will be a clearance fit, and in between these will be transition fits. So defining the tolerance zone of the hole to be fixed and then selecting the tolerance zone range for the shaft, whatever the fit may be, is called as the hole basis of defining fits. Important to note over here is one limit, whether the upper limit or the lower limit coincides with the basic dimension. In this case, the lower limit coincides with the basic dimension. Also over here, the lower limit coincides with the basic dimension. This is a prerequisite for having a shaft basis or a hole basis system. Go through the definition of fits. How do we define a fit for an application? So the basic procedure, the basic steps involved are to first define the tolerance grade. So this establishes the size of the tolerance zone. And the second step is to define the fundamental deviation which locates the tolerance zone relative to the basic size. We'll understand this also along with multiple examples to drive home the point. So what are tolerance grades? Tolerance grades are basically a table of tolerance values which have been established as standards for standard manufacturing process for various nominal values of dimensions. These tolerance grades are generally denoted as ITX, where X can be anything from 0 to 16. 0 indicates very fine tolerances. We can say that these are gauge tolerances, the tolerances which are used for measuring equipment, till 16 which are open tolerances, tolerances used in casting, forging kind of processes. So these are tolerance grades which are used for various manufacturing processes which have been established as standards for various nominal dimensions. So IT over here indicates international tolerance. So to find out the tolerance range for our application, we basically refer a table of nominal size ranges for various grades which provide us the tolerance range values. For our usage, we will be using the ISO 286 standard, which is commonly used in the industrial practice. Next is fundamental deviation. So as we have already defined, fundamental deviation is the smallest deviation between the upper and lower deviation, which basically tells us where does the tolerance zone located with respect to the basic size. So for different applications, for different fits, clearance fits, interference fit, transition fits, there are different fundamental deviations which have been established by standards. So we need to specify one such fundamental deviation for our application, whether it is for the shaft or whether it is for the hole. So a wide range of fundamental deviations have been established as a standard from which we can select for establishing the fit, whether it's clearance fit or interference fit. Generally, while denoting the fundamental deviation, capital letters indicate hole basis and small letters indicate shaft basis. So idea over here is to refer the fundamental deviation tables in the same standard, that is the ISO 286 standard, and find out the fundamental deviation for our application, whether it be for clearance, whether it be for transition or interference. We'll understand this in detail with the help of examples, with the help of multiple examples. So here is a snapshot of the tolerance grade table for various international tolerance grades from IT01 to IT18 for various ranges of nominal sizes. So if you have, say, a nominal size of 50, then we need to look over here up to and including 50. For this, IT01 to IT18 varies from 0.6 micrometer. The unit over here is micrometer, which is very fine tolerance, varies from 0.6 micrometer till 3.9 millimeter. So IT01 indicates gauge tolerances, IT18 will indicate very open tolerances associated with processes like casting, forging. And here is a chart of fundamental deviations which tells us the various fundamental deviations which can be selected in the standard. So for the hole, they are generally denoted with a capital letter A, B, C, D all the way till ZC. And for the shaft is generally denoted with the small letter, as you can see over here. So the fundamental deviation over here is defined by this delta F value. So if we consider the tolerance zone D, it is located at the fundamental deviation of delta F from the basic size. If you want to find out the shaft basis and the hole basis, then we can see the tolerance zone of H, which is located attached to the basic size. So capital H is the hole basis and small h over here, this one right here, is the shaft basis tolerance zone. So we can use this capital H and small h when we want to have either a hole basis system or a shaft basis system, which basically fix the tolerance zone with respect to the basic size. Before we go on to the examples to understand the definition and decoding of fits, let us have a look at these three scenarios. So in the clearance fit case, this is the tolerance zone for the hole. This is the tolerance zone for the shaft. The pink color zone is for the shaft. The green color zone is for the hole. So the size of the tolerance zone is defined by the IT grade. So ITX will define the size of the tolerance zone for hole and shaft. And we have lower deviation and upper deviation for the hole, which is defined over here LDH and UDH. We have upper deviation and lower deviation for the shaft, which is defined over here UDS and LDS. And in these two, we can say that the fundamental deviation is LDH because that is smaller, and over here the fundamental deviation is UDS because that is smaller. Now if we apply the same idea for transition and full interference fit, we can see over here. So this is for the hole, the green color tolerance zone for the hole. This is for the shaft. This is a transition fit because it is not purely clearance, it is not purely interference, it is a transition fit. Here LDH is equal to 0 because the lower limit is resting on the basic size. So LDH is equal to 0, and over here UDS and LDS is the smaller one. So in case of the shaft, the fundamental deviation is LDS. In the case of the hole, the fundamental deviation is LDH, that is the lower deviation. Going on to interference fit, we can see the locations of the tolerance zones. So the basic size and the tolerance zone for the hole is almost centrally located, with UDH being the smaller distance. And For the shaft, the LDS is the smaller distance. Hence, the fundamental deviation for the hole is upper deviation. The fundamental deviation for the shaft is lower deviation. So this gives us an idea as to what is lower deviation and what is tolerance grade for different scenarios.